or LHC, is the world's biggest and most potent particle accelerator. The Center for European Nuclear Research, situated at the Franco-Swiss border, was founded in 1952 to help humanity understand the universe. The organization is known for providing ace physics research focusing on understanding atoms. Using a ring of superconducting magnets, LHC is a helpful device for scientists as it is used to test theoretical assumptions in particle physics, especially those linked with the Standard Model. Though the Standard Model can explain particle physics discoveries, it has its limitations as various problems remain unsolved. Such issues include the components of dark matter and dark energy. And the reason matter is more than antimatter, the scientists hope that LHC will answer those questions. Now that we know what CERN is and its most significant invention, let's talk about what is going on within the walls of this massive laboratory. Recently, physicists announced that they had found 3 significant unidentified particles. The largest particle accelerator in the world reportedly discovered 3 new large particles while looking for information regarding the mysterious forces that hold together subatomic particles. The observation of the 2 particles, a new type of pentaquark, and the first pair of tetraquarks took place at the CERN lab in Geneva on the day the Large Hadron Collider was reactivated again after 10 years of rest. The reactivation, following a series of maintenance and upgrades, offers a global network of scientists another chance to look for strong force that binds together the nuclei of atoms. The strong force is part of the 4 forces that regulate particles decaying, which includes the electromagnetic forces, gravity, and the weak force. Interestingly, the reactivation of the LHC is just a day before the 10th anniversary of the Higgs boson discovery, a milestone achieved by CERN in 2012. This particle helped to establish the Standard Model, which accounts for the basics of particle physics. The Higgs boson assumed to have existed before the beginning of the universe, shortly after the Big Bang 13.7 billion years ago, helps give all of its matter to mass. It is named after the Nobel Prize-winning physicist who theorized it. The quarks are elementary particles in 6 types: up, down, strange, top, and bottom. These particles usually come together in 2s and 3s to form hadrons, like the protons and neutrons making up the atomic nuclei, an elementary building block of the universe. These particles usually disengage quickly and were difficult to detect before the upgrade of the LHC. They can occasionally combine to form the 4-quark, 5-quark, tetraquark, and pentaquark particles. Scientists predicted these exotic hadrons around 60 years ago, around the same time as the conventional hadrons. Still, it has only been in the last 20 years that LCH and other experiments have been able to observe them. However, the Higgs and the quarks particles are just some of the discoveries of the LHC. Another of its breakthrough discoveries are neutrinos, also known as ghost particles. This achievement was made with the joint effort of CERN's Forward Search experiment. Neutrinos are nature's most mysterious particles that travel at near light speeds. On the other hand, they are the most common particles in the universe. Every second, almost 100 trillion of neutrinos travel through your body harmlessly. However, they are challenging to see as they don't relate with other particles frequently. But this doesn't mean they didn't interact with other particles. The rate at which they do could be higher. But what are neutrinos and why are they making a fuss about them? The name neutrinos depict that they are neutral. They are the most particles in the universe that has mass, but scientists cannot measure their mass due to their smallness. To get measurements of neutrinos, an international scientific organization designed and constructed the Karlsruhe tritium neutrino experiments in Germany to get the measurement. The scientists determined the top limit of neutrino mass to be 0.8 electron volts or eV. An electron volt is the number of kinetic energy acquired by an electron when it is accelerated by a volt. Initially, measuring mass with energy units may sound surprising, but Albert Einstein's description of mass and energy by his famous equation of E equals mc squared shows that they are 2 sides of a coin. Also, tiny particles are measured in eV because the kilogram conversion is so small. 0.8 eV is about 1.4 times 10 minus 33 kilograms. To make it more straightforward, electrons are 10,000 times heavier than neutrinos. After the Big Bang, a large number of neutrinos were created, and many more are still being produced today in the form of star nuclei, particle accelerators, and atomic reactors. They are present both during radioactive decay of substances and supernovae. Although neutrinos interact with the weak force that governs radioactive decay, they do not link to the strong force that holds atomic nuclei together. Even though neutrinos remain a hard nut to crack for scientists, they believe that they are more than protons in the universe a billion times due to their neutral attributes. Their neutrality enables them to pass through a square centimeter of your body without you knowing. In contrast to other particles, which may be deformed with their interactions with other matter, most matter-like objects pass through neutrinos as if passing through clear glass. They carry a wealth of information as they travel across space. And studying them gives us more understanding of the universe's origin. This ghostly particle was found when scientists unraveled the mystery of beta decay. Beta decay is a mystery because it seems to break two fundamental physical laws, the laws of energy conservation and the law of momentum conservation. They found that the final particle configuration contains too little energy during beta decay, and a proton remains static instead of moving in the opposite direction, like the electron. In 1930, scientist Wolfgang Pauli proposed that an additional particle may be emitted, bringing the lost energy and momentum with it. However, Pauli, knowing very full well that the particle he had proposed could not be discovered, penned down, "I've done something very bad today by proposing that a particle that cannot be detected. It is something a theorist should never do." The sun emitted many neutrinos, many of which ended up flooding the Earth. Scientists set up different detectors to detect those neutrinos, but they only detect 1/3 of the expected neutrinos. Scientists have tried hard to address this problem, but their efforts have proved abortive because they are missing one fundamental fact. Neutrinos come in three types: the ordinary neutrino, the muon neutrino, and the tau neutrino. As they travel between the Sun and Earth, neutrinos bounce between these three forms, and this explains why the earliest experiments to detect the neutrinos only detect 1/3, missing the other 2/3. The CERN discovery of neutrinos was the first time the particles were identified within the LHC or any other accelerators. As expected, the discovery sparked excitement as it opened a new door for scientists to investigate the subatomic world. Also, the ability to discover neutrinos in the LHC will help scientists in learning more about the role they need to play in the universe. Before the LHC discovered neutrinos, scientists tried several trapping methods. There was the super Kamiokande used by Japanese scientists, the ice cube detector at Antarctica, and the mini boon detector at Fermilab. Using the Cherenkov radiation technique of the super Kamiokande, they could detect neutrinos. This technique runs on the same principle as an aircraft, faster than the speed of light. The particle is designed to go through a light speed medium, leaving behind a faint blue glow. Even though these experiments can detect the sign of neutrinos emitted by the sun, various problems remain. For instance, scientists cannot differentiate the types of high-energy neutrinos formed when these particles collide in a conventional particle accelerator. To detect these manufactured neutrinos, scientists from the Phaser collaboration created a new detector called Phasery. This new detector comprises solid metal plates of lead and tungsten with many layers of an emulsion substance that detect lights between them. At first, the neutrinos collide with the atomic nuclei in the thick metal plate to form their particles byproduct. The next phase is the emulsion, whose action is similar to conventional photographic film. The emulsion reacts with the neutrino leftovers, imprinting the particles and tracing the shapes as they travel through them. The scientists then create the emulsion to investigate the trails left by the neutrinos' particles. Not only did the new method provide information that will be useful in establishing that some of the marks were caused by the particles, but it also enabled scientists to differentiate between the three types of neutrinos. But scientists are still looking for a better method. They are looking for an alternative that will be more sensitive to neutrinos detection and able to differentiate between neutrinos and antineutrinos, which are neutrinos' antimatter counterparts. The high luminosity upgrade given to the LHC is expected to increase the rate of collisions that appear in the detectors significantly, which means more measurements of more particles as they decay. The upgrade has increased the collider's power tremendously from its previous energy of 13 electron volts to 14 TeV. This implies that as the protons fly around the 27-kilometer long collider ring, each batch will carry the energy of 360 tons of passenger trains traveling 100 miles per hour. From 2029, the upgraded LHC's collision is expected to increase from 30 to 140 times and will run around the clock for around 4 years at 13.6 trillion electron volts. Also, researchers hope to learn about undetected dark matter from the LHC operations as time progresses. The CERN isn't left out as they aim to understand more about particle production and decay processes that create matter and antimatter in the LHC. Do you think the LHC can meet all these expectations? Let us know in the comment section below. Thanks for watching this video. See you in the next one.